So now this form is for any water flow in the subsurface, whether or not it's fully saturated or not. So to do that, the first thing we're going to do is just look at the unsaturated form of Darcy's law. Okay, so what is Darcy's law for saturated conditions? And well, I'm gonna let's start off with your answer. So Autumn did the big Q, negative K A dH over dL. And if I do Q over A, that's equal to little q, and that's negative K A dH dL. So this is for saturated media, right? And this K here is K sat. It's the saturated, it's the hydraulic conductivity for fully saturated conditions, right? So how did we have to change hydraulic conductivity for unsaturated conditions? What do we have to do? Right. So so for unsaturated, we have to calculate this K effective, right? And that was given by the relative hydraulic conductivity times K sat. And you guys just went through all kinds of blood, sweat, and tears to figure out that this K sub R is a function of the pressure head, right? Okay, so how do you think we modify Darcy's law for unsaturated zone flow? Yeah, exactly. We're just going to take this K effective and we'll plug it in here, and I'm just going to write it out the long way. So first, I'm just going to say we could also write K sub R is a function of psi. So Darcy's for unsaturated little q is equal to negative KR, which is a function of psi, times K sat, our normal sort of saturated hydraulic conductivity, times dH over dL. And I'm going to just, the only thing I'm going to do here, and we never write this, and I won't write it again, but just to illustrate a point, I'm going to put this here so that we recall that, remember, the head is equal to Z plus psi, right? So our head is a function of psi too. H is a function of psi. So the psi is playing a role in two parts of this equation now. In the relative hydraulic conductivity, as well as in the head. And if we look back to regular Darcy's law, this should not have an A here. The A is over here. Okay, if we look back to Darcy's law, for saturated material, what it says is there is a linear relationship between the gradient, the head gradient, and the discharge. And the slope of that line is equal to the hydraulic conductivity. This equation is a linear equation, and it says the discharge is linearly related to the gradient, head gradient, and the slope of that line is the hydraulic conductivity. Now let's look at unsaturated flow. And here we've got a head gradient, right? And we've got a discharge, but this thing that relates them is not constant. There's not a constant slope, because as we change head, then we're going to change K sub R. So there's no longer a linear relationship between discharge and head gradient. So unsaturated Darcy's is what we call non-linear. Because K effective is not constant. It depends on my head. All right. So as head gradient changes, Q will change. Or the relationship K sat or K effective will change. All right. So two things about this. This is going to make life much, much harder when we're trying to solve any equation for unsaturated flow. And we'll discuss this when we look at Richard's equation. But what we end up with is what we call a nonlinear partial differential equation. And the fundamental reason is because there's not a linear relationship between this head gradient and the discharge. Okay, so I'm just going to present sort of Richard's equation here without deriving it. The derivation method is exactly the same as deriving the confined aquifer groundwater flow equation. The only difference is where we, instead of inserting saturated Darcy's law, when we talk about the fluxes in and out, we insert the unsaturated Darcy's law. So here's what the unsaturated zone differential equation looks like. C sub m plus R times S sub S, and we'll define all of this stuff here. Times dH dt. All right. So this over here now, for our confined aquifer equation, we only had S sub S, but this in the brackets here, this is my storage. This is essentially my storage. All right. This guy here will define, I'll write it out in a second. This is my saturation level. And this is what we call the moisture capacity of the soil. It's basically the slope of your characteristic curve. It is it is the derivative of the volumetric water content per change in head. I'll define them all in a second, but just so you know, this is the storage over here. All right. Then we get over to our spatial derivative. So here d dx. And now this is where the main difference is. Kr times kx dh dx. And this doesn't have to be a square bracket. It can be a regular one. Doesn't really matter. All right, and now these are going to be for every direction. So d dy kr times ky times dh dy plus d dz kr kz dh dz. All right, so here C sub m is equal to d theta sub water dH. This is basically it's just the slope of your characteristic curve at a given location of psi. All right. We call it the moisture capacity. I don't know why. R is my saturation. So that was volume of water over volume of voids. And SS is the normal specific storage. Rho water G beta sub water plus N. Oh no, beta sub porous media. So this term over here is my storage term now. And it basically describes how much a unit change in head, how much water it takes to produce a unit change in head. All right, and so it's got saturation for the filling or draining of pores, and it's got this C sub M, which is essentially how does this change in moisture level then affect the head. So let's look at what happens to Richard's equation as we get to the saturation point. So as a soil saturates, so as my soil saturates, so first of all, let's just think about storage, the storage term. Which is C sub M plus R times S sub S. And recall that C sub M is equal to the change in volumetric water content per change in head. Okay, so as I get close to the saturation point, or when my soil becomes saturated, what happens to theta sub W? What is theta sub W when my soil is saturated? It's equal to porosity, right? Once I become saturated, does it change at all? It never changes. So what is the value of this derivative if this is never changing? Yeah, remember this says the change in theta sub W per change in head. Well, if theta sub W is not changing, the change in theta sub W is 0. So this goes to 0 at saturation. Remember that R is the volume of water over the volume of voids. What happens to R at saturation? What's the value of R at saturation? 1. So this goes to 1 at saturation. So if this goes to 0 and this goes to 1, then the whole storage term goes to S sub S at saturation. This is fantastic news. This is reducing to the exact same storage term we had for our fully saturated aquifer equation. So when we reach saturation, the storage term of Richards goes to the fully saturated equation automatically. That's great news. Okay, let's now talk about, let's just do one of these spatial derivatives. The spatial term. And so this was d dx, for example, of k sub r, ks dh dx. Let me just make this kx. What happens to k sub r at saturation? What's the value of k sub r at saturation? Yeah, k sub r varies between 0 and 1. Remember, the highest value of hydraulic conductivity we can have is when we're fully saturated and all the pores are transmitting water, right? So k sub r goes from 0 to 1. So at full saturation, this thing's at 1. In that case, this term reduces to d dx kx dh dx. So all these spatial derivative terms, they also reduce just to the confined aquifer equation. So this is the fantastic thing about Richards equation. It works in the unsaturated zone, and it just automatically converts to the saturated equation in the saturated zone. So Richards that means Richards equation is valid. Oh, I put the apostrophe on the wrong side. This is very important. Reviewers will get after you if you don't put your apostrophe on the right side when you write Richards equation. So Richards equation is valid anywhere I want to look. I don't have to be in a confined aquifer or an unconfined aquifer. I can be in the vadose zone or in a fully saturated zone. It works everywhere. It's beautiful. We love it. Here's the problem. I want to go back and think about this. So in the anatomy of a partial differential equation, we've got 3 pieces here. We're going to call head the dependent variable. All right, 1. And this is what we're at. This is the thing that we're after. We want to know groundwater head. And groundwater head is a function of x, y, z, and t. All right, these are called the independent variables. The spatial position does not depend on the groundwater head. It is what it is. All right, so these are the independent variables. So we want to know head at all of these independent variables, or as a function of these independent variables. And then the third piece here are what we call parameters. So this, and all of these are what we call parameters. These are properties of the system that control the response between the dependent variable and the independent variable. Properties that control, let me zoom in, control the response between the dependent and the independent variables. All right, they're just basically what this says, you know, in more simple terms, is that the way in which head varies as a function of space and time depends upon the hydraulic conductivity and the storage coefficients, right? So that's sort of the anatomy of a partial differential equation. Now, I'm gonna just write these. I just want to look at the spatial term down here, and I want to illustrate the difference between Richards and the normal groundwater flow equation. Here we are. I'll write it here. So Richards, we have d dx, and I just want to write it this way: k sub r, which is a function of psi, times ks times dh, which is a function of psi, over dx. All right, and then the saturated zone spatial derivative would be this: d dx ks dh, which is still a function of psi, dx. So there's a subtle but incredibly important difference between these two. And the difference is that in the Richards equation, my parameter set depend upon my dependent variable. That is, in order to know what my relative hydraulic conductivity is, I already need to know what my head is, but I'm trying to solve for head, right? I'm caught in this trap where I'm trying to predict my dependent variable, but my parameter is a function of that. Over here, my parameter is independent. So here my parameter does not depend upon my dependent variable. And this is a really big difference. This guy over here is a linear differential equation. I just need to know the value of K sub S, and then I can predict K DH, or I can predict my head. This one is what we call a nonlinear. Oops. And these ones are really hard to solve. I've got to keep trying to predict my change in hydraulic conductivity as my head changes. So while Richard's equation is super elegant and gives us a single equation that would be able to describe groundwater flow in all systems, unsaturated and saturated, because of this nonlinearity, it becomes really hard to solve. Like without a computer, basically impossible. There's a few solutions. And even with a computer, we have to really, really like iteratively change the solution. So we calculate a new head, then we calculate a parameter, and then we recalculate the head based upon this new parameter. And then we got to update the parameter, and then we update the head. And we keep doing this back and forth until they stop changing a lot. And it just takes a long time. So my take homes for you is that, well, one of my learning objectives of this class is that we learn to read these partial differential equations. Here we can go through and we can think of some things about this Richard's equation. Is it transient or steady state? What do you think? Transient or steady state? What does steady state mean? Yeah, so is this equation here, is this transient or steady state? It's transient. This is not equal to zero. The head is changing with time. Is it homogeneous or heterogeneous? Heterogeneous, why? Oh, yep. Why is it heterogeneous? Yeah, it's inside the spatial derivative. That means it's not constant with space. It changes with space, right? And then we've got this KR term. So inside of here is unsaturated Darcy's law, right? And this KR term is a function of the head. We're not going to solve Richard's equation. We're not going to use it very much, but I do want you guys to have seen it. It gets used a lot in other We sort of hold it up as the holy grail. In my lab, we use a really specialized model that will simulate Richard's equation. It can be done, but for most people, most of the time for groundwater, they don't want to deal with Richard's equation. It's too computationally expensive, and so most of our other mechanisms try to get around having to use Richard's equation. What I want you guys to know is what I want you guys to be able to see groundwater equation, saturated flow equation, and Richard's equation, and tell the difference between the two. That's my learning objective for the class, is for you guys to be able to start reading these PDEs and at least understand what kind of system they're describing. As you go on, if you go on in science and engineering, you'll hear a lot about linear and nonlinear partial differential equations. And a lot of people don't actually know what, a lot of people say, I've heard, I can't tell you how many times I hear somebody say that the heterogeneous, three-dimensional, transient, saturated groundwater flow equation is nonlinear, and that's not true. They're not correct. That's a linear partial differential equation. It's not, doesn't mean I can solve it, but it's linear. Richard's equation is nonlinear. And the fundamental difference is this: the parameters depend upon the dependent variable in this nonlinear PDE. All right, some last quick things that I want to talk about here in the unsaturated flow, and that is that let's go back to unsaturated Darcy's. And maybe I'll draw a little chunk of porous media here to illustrate our next point. And we've got water. Sort of in, we'll say that, you know, we're partially saturated, so we got water only in some of these pores here. And water is flowing. We've got Q flowing in this direction. Okay, so what is the relationship between velocity and the Darcy flux in a saturated porous media? How does the fluid velocity and what's the relationship between the fluid velocity V and Q? Right, so the velocity is equal to the flux over the porosity. And why did we have to do this? Do you guys remember why we had to divide by porosity? Exactly. The flow's only able to go through the pores. It doesn't go through the grains. So we had to divide by porosity. Okay, so what do you think the relationship between the Darcy flux and velocity is in unsaturated media? Yeah, so now the area available for fluid flow is only those saturated pores. It's not just the pore space, it's the saturated pores. So now my velocity in my unsaturated media is equal to the Darcy flux divided by this guy. What happens to this equation when I become fully saturated? Exactly. It turns into Q over N at full saturation. Theta sub W goes to N at full saturation. So this equation holds at saturation or at unsaturated flow. What this means is that the fluid velocity is actually faster the drier your soil is. It's kind of mind-blowing. It's just because the water's having to, it's like, you know, when you've got a hose and you put your thumb over half of the hose, the water moves faster, right? All this means is that my thumb's moving over more of the hose. I have to move the flow through a smaller and smaller area. So when at the beginning of an infiltration event, let's say I have a really dry soil and I have a rain or a snow melt that starts, as that first water starts to trickle into the soil, it moves really fast because it's moving through that really dry soil. And then as we fill more of the pore space, the fluid slows down.
Does that have more to do with like pressure or the soil grains themselves?
This particular response is, so Finch had a great question. He was asking, does that have to do with pressure or the soil grains? And this particular response that we're discussing, Finch, only has to do with the fact that there isn't any water in the soil. And so that water's moving through a really small area, just right along the soil grain boundaries. We also have increased infiltration because we have these increased capillary pressures pulling the soil in, or pulling the water into the soil, sorry. But this particular response here has only to do with the fact that the drier the soil, the water kind of moves into these really thin sheets. And so the water is moving very fast. As it wets the soil up, it slows down. So let's talk about flow in unconfined aquifers and why they are different than a confined aquifer. So let me, I'm going to draw a sloping land surface. Goes down to a river. My drawing's terrible right now. we're looking at here's some trees, so we know we're at the land surface here. And we got a water table that is sloping. And meeting the river here. And then at some depth down here, we've got a confining unit. Having a real problem drawing straight lines at the moment. And there's a groundwater divide here at the middle of the river. And there's another groundwater divide here. Let's say this is the ridge top. And the water table flattens out here and goes down. Okay, so I could draw a basic flow net here. So orange will be my head contours. This isn't going to be a super good flow net, but it'll give us some indication of what the head contours look like in this kind of flow system. And my flow lines would do something like this. Put one more down here. Okay, so this is general, basic idea of what flow looks like in an unconfined aquifer. And I'm going to point out a couple things. The head in the aquifer, if I was to measure it here at this point, this would be H1. And then the head, or the height of the water table here, is H2. Okay, so some observations about this aquifer that are important to make. The first one here is that H1 is not equal to H2 here. If we're going to have flow in an unconfined aquifer, our water table height has to change. And the important implication of this is that our aquifer thickness is always changing in an unconfined aquifer. So our aquifer thickness changes with distance. Anytime we have flow in an unconfined aquifer. Any change in head in an unconfined aquifer will result in a change in thickness of the aquifer. So that's big change number one. Big change number two, or difference, is that our storage is different. All right, let's go back, way back to before exam one. What are the forms of storage in an unconfined aquifer? How do I get water out of an unconfined aquifer? What are the different ways? What is our storage in a confined aquifer? We just talked about it with the Richards equation. Where do we get water? What is the confined aquifer storage? Right. So it's the compaction of the sediments and the expansion of the water, right? That's the form of storage in the confined aquifer. The only place we're really releasing water from storage is by compacting sediments and expanding the water. So that was this SS. How else did, okay, so SS times H, this is compaction of porous media and expansion of water. How else do I release water from storage in a unconfined aquifer? This is like probably the fundamental difference between the two. If I drop the head, I release storage by dropping the head in both. But if I drop the head in an unconfined aquifer, what am I doing? If I lower the water table here, what have I done? I've reduced the thickness, but I had to drain the pores to do that, right? In a confined aquifer, as long as a confined aquifer stays confined, I never drain pore space. It's still full of water. But this guy, if I reduce the head, I drain pore space. And that was this, we had to add the specific yield to this. So this was draining the pore space. Okay, so aquifer thickness changes with distance and with head, all right? And the storage is very different. We drain pore space. When we drop the head, we're draining pore space. And we made some calculations. There's actually a lot more storage in an unconfined aquifer because Once we move to that place where we're actually draining pore space, then we're, like there's a lot of water in there that we can drain out to drop the head. I want to point out one other thing here, and that is that here at the top and at the bottom of this aquifer, we have vertical flow. And in the middle here, horizontal flow. So my flow in an unconfined aquifer is usually vertical at the recharge areas. It's usually vertical at the groundwater divides. Let's put it that way. And for all of my flow paths, I have this, except for right in the middle, I've got some component of vertical flow. Like this flow path, there's, if I were to take this guy and split it into its components, there's my, I'm going to keep my colors the same. Ooh, marker. There's my vertical flow. There's my horizontal flow. So, near the water table, most of my flow is in this vertical direction, and I have sub-horizontal. But then, sort of in the middle down here, very little vertical flow. Okay, so the fact that the aquifer thickness changes with head makes solving the differential equation for even writing the differential equation for the unconfined aquifer really complicated. And rather than get lost in those details, I just want to talk about what we do to deal with it. All right. So the first thing we're going to do is tackle this these flow lines. And we're going to make what's called the Dupuit assumption. So this one is big enough. To get its own. And the basic idea is this. So in that last figure, I'd drawn this unconfined aquifer with a water table, and I'd given this water table a pretty big slope in the vertical direction. But in reality, the earth is really, really flat, and unconfined aquifers are very flat. And so the Dupuit approximation says this. So my flow, if I was to take a flow vector and draw it here along the water table, there should be a tangent line to this water table. So I'm going to just fail utterly in drawing one of these, but it looks something like this. This is my true flow along the water table, Q sub S. And Darcy's law for this would say Q sub S is equal to negative K dH ds, where ds is the direction of flow along this. ds is the direction along this vector here. And all the Dupuit assumption really says is, you know, if I was to take the horizontal component of this, Q sub X, so here I'd have Q sub X is equal to negative K dH dx. All that the Dupuit assumption says is Q sub X is pretty close. Q sub X is pretty darn close to Q sub S. And so this is the Dupuit assumption. It says the difference between these two is not that bad. So let's just say that all the flow is horizontal. And so what this means is, even though in the real world, we know that our flow paths are doing something like this. What the Dupuit assumption says is, but we can approximate them as things that are doing this. And this is okay. This is definitely okay in the middle of the aquifer. Right? Because we can see it right here. I've got horizontal flow, even in the real world, and the Dupuit assumption is doing really good. It's not very good. It's not very good over here. So it's not great on the edges of the aquifer. It's only valid where the water table slope is small. Which most, most flatland applications of this are totally fine. All right. For poor Jenna, who's doing hydrology up in the mountains, Dupuit assumption kind of sucks. But all right, so it has some limitations, but the main thing is it allows us to simplify our unconfined aquifer equation quite a bit. And to come up with some actual solutions to it. So the Dupuit assumption leads to the Boussinesq equation. And this is the equation for unconfined aquifer flow subject to the Dupuit assumption. All right, and it is this. The storage S dH dt is equal to d dx k, I'll put an x here, times h times dH dt plus d dy times k y times h times dH dy. Yes, thank you, Autumn. Good catch. So the main difference here, is this guy. We have this extra H term. We're saying that the head or the thickness of the aquifer varies spatially. Also, there's no vertical flow, so there's no ddz. It's only x and y. And recall that S was the specific yield plus the specific storage times the height of the aquifer. There's one more simplification here that that we can make, and that is by remembering that let's say that the transmissivity is equal to K, and that was the times the thickness of the aquifer, right? But here that's H. So we can move this and plug it in here. So this gives us S dH dt is equal to d dx t dH dx plus d dy t dH dy. Now this has the exact same form as our confined aquifer equation, except that instead of K right here, it has T, the transmissivity. And the transmissivity takes into account both the hydraulic conductivity and the thickness. And this equation, yeah, Finch?
Why is it just T and not like TX or TY?
Oh, Finch had a great point. He said, they said, why is it just TX or why is it just T? Why isn't it TX or TY? And Finch, that is a great point. TX, TY. What, but now that you ask the question, Finch, you're going to get put on the spot. What would it mean if I didn't have a T sub X or a T sub Y in that equation?
It would mean that the K's are the same.
They're not, yeah, they're not exactly, they're not dependent upon the direction. So what Finch said was that they would, the K or the T would be the same between TX and TY. And yeah, that means, and they don't depend on direction, so it's isotropic. Okay. This one gets called the aquifer equation. And probably the most well-used groundwater model in the world is ModFlow, written by the USGS, and it has changed over the years, but the original ModFlow code solved this equation. And this is still how most people model groundwater systems, with this equation. So this is probably the most used groundwater equation. And the reason why is it can be used both for a confined and an unconfined aquifer. You just need to know the thickness of the aquifer and the hydraulic conductivity. But what needs to be remembered is that this equation is based upon the Dupuit assumption. We've assumed only horizontal flow. This is a reasonable assumption for most situations, but it is important to remember that it's assumed that all flow is horizontal. There are some ways that ModFlow tricks this equation to have vertical flow, but it's not very elegant and it's not actually very correct. Okay. So why do we use the Boussinesq equation? Well, the main reason is it reduces to this like more simplified aquifer equation, and we can start to get some solutions to it. It's linear, all right? It's not a nonlinear equation, or it's subtly nonlinear if you do it right. But we can also start to derive some actual analytical solutions. So we'll talk about one analytical solution today to the Boussinesq equation, just to give you a flavor. So let's we actually have a research project where we're working on something where this solution is not a terrible one to use. So We have a research project down in Riverton, Wyoming. And this is, here is the land surface. And on either side, we've got this, we've got a river. So this is the, I'm gonna exaggerate things, sorry, so that it makes it easier to draw. So we've got the Little Wind River on this side, and we've got the Wind River on this side. So we've got two rivers. And let's put a bottom boundary here. And this river's height here is H naught. And this river's height is H sub L. And this distance, this is the X direction here. And the total distance out here is L. All right, so at our site in Riverton, so we've got this water table that stretches between these two rivers. And we have rain and infiltration and recharge across the mesa. So this is my infiltration rate, N, and it's constant across this mesa. And in Riverton, there was a bunch of uranium mining, and they had a big uranium mill tailings pile here. And that uranium leached down as part of the rain, and it hit the groundwater table, right? And so a fundamental question would be, well, which river is it going to go to? And that would depend on the shape of this water table, right? And in particular, somewhere here, the way I've drawn the water table right now, and I just drew it, right? I have no math behind it. There's a water table divide right here. And what I mean by that is anything on this side of this divide will go down towards this river. Anything on this side of the divide would go down towards this river. So these flow paths tend to go this way, and these flow paths would go that way. And this divide occurs at the maximum water table height, right? It occurs wherever my water table height is the highest, H max. All right, so for this, so I've got my, now some boundary conditions that I'm gonna write. So H is equal to H naught here at X is equal to 0. So this is X equal to 0. This is X equals to L. So my groundwater head is equal to H naught at X is equal at X equal to 0. That's my left-hand boundary condition, this guy right here. My right-hand boundary condition, well, my head would be equal to H sub L at X is equal to L. And my infiltration rate or recharge rate N, we're just going to say is greater than 0. So these are my boundary conditions. And we can derive an analytical solution to the Boussinesq equation. All right, this is why the whole reason why we develop these damn equations is so we can solve them, all right? Given these boundary conditions. The height of the water table is equal to H naught squared minus H naught squared minus HL squared over L times X plus N over K times L minus X times X all to the 1/2. This equation here allows me for any X, for any position here, any X to calculate the head, right? So I can come here at any one of these X's and I get a calculation of the head or the thickness of the aquifer, the water table height. Now, what is fundamentally important here would be, well, what's the distance? What is the distance to my water table divide? That would tell me my distance to the water table divide, XWD, would tell me which river this tailings pile would go to, or this leaking of uranium would go to. So I can take the derivative of this equation, set it equal to 0. That will tell me where the water table divide is, and then I can solve for X. And I'm going to spare us the details of that. So this equation would allow me to calculate the head at any point X. And this equation here allows me to calculate exactly where the water table divide between these two bodies of water is. This water table